Hello everyone, welcome to lecture 7 of the online course on modern display technologies, flat panel display. Today's lecture will be on fundamentals of color science. So here is the lecture outline. So in this particular topic of color science and engineering, in the previous lecture we have introduced the two most relevant color systems, and then we also discussed about photometry, the different units of measurements which are involved in this particular science. Today we will basically look into more details of eye. It is important to understand human eye little better because we are dealing with display technology. We will also look into the blue and the violet light effects, okay, and we will see the 3D perception and displays in this particular lecture. So let us begin with color science and engineering, focusing on eye. Okay. So all of you have known this from your school days, that incoming light basically passes through several structures. Okay. The first will be the cornea, which does the primary refraction at the air cornea interface. Okay. Then you have this aqueous humor followed by lens, and then you have vitreous humor. These are different fluid in your eyeball that basically guide light to retina. So this is where the image is formed. So this is typically how a cross section of an eye looks like, and here you see the two instances of how a far image or a far object's image is formed in human eye, and here a new like relatively nearby object's image is formed in the retina, right. So there are a couple of other factors that you see here in human anatomy, eye anatomy, that one is very important, which is the fovea, this particular part, and the other one is this optical disc. So this is where the nerve point is. Okay. So this basically sends also signal to your brain. So the eye lens, what is the functionality? So any lens has got a refractive index which is used to bend light. So eye lens also has a refractive index of n equals 1.42, which is higher than the surrounding media. Okay. Then the cornea, aqueous humor and vitreous humor, okay, these have refractive index ranging from 1.33 to 1.37. Okay. So here you can see that the basic purpose of all this fluid and the lens is to basically make a clear image onto your retina, and the shape of the lens also get changed when you are looking at a far object or when you are looking at a near object. Okay. So you can see the adjustment in the lens shape in the two cases. Here the lens is much flatter, here the lens is much wider. Okay. And this can be done using this ciliary muscle, which can stretch the lens, okay, or it can relax and make it like this. So whenever there is a image being formed, okay, you can basically apply the Gaussian lens formula. So if you consider this eye's optical system, here you can write 1 over d1 plus 1 over d2 equals 1 by f. This is the popularly known lens formula. Here d1 is basically the distance from the object to the eye's lens, basically this distance, okay, and d2 is basically the distance of the eye lens to the retina, which is typically 17 mm, okay, and f is basically the focal length, okay, of your lens, right. So when you do this, you basically can obtain what is the image formation. Okay. So these distances and the focal length is related using this particular formula. Now one thing you can observe here is that the image that forms on retina is basically reversed. That means it is upside down and it is right to left. However, when the interpretation is done by brain, okay, it can recognize the images in their normal orientation in real space. So, that is the beauty of God's engineering, right. So, another thing to notice here is that when the object viewed is at far distant, okay, it is placed far away, you can see eye's lens becomes basically flatter, which is shown here. On the other hand, you will see when the object is very near, your ciliary lens basically contract the eye's lens, that basically increases the curvature, so that you can focus the light coming from the nearby object, which is basically seen here. So, your retina basically receives the incoming photons and it can convert this into biopotential signal. So, you have optic nerve that basically takes that signal to your brain. So, after some processing within the eye, these signals are basically transmitted through the optic nerve to the brain, and that is interpreted by the viewer. So, if you carefully see, the retina is basically a multi-layer structure that can be subdivided into three parts. One is photoreceptor, then you have connecting nerve tissues that includes outer and inner plexiform and nuclear layers and ganglion cell layers, and also it has got optic nerve. So, if you look into the anatomy of human eye more carefully, so we are basically zooming into this red box. So, this is how it looks like. So, there are basically two kinds of photoreceptor cells in eye which are most important in vision, and these are called rod and cone cells, which we briefly discussed in the previous lecture. So, these names are basically given based on their shape. So, here you can see these cells are like rods, so you call them rod cells. These are like cones, so these are cone cells. Okay. So, this is the entire thing is retina. This portion is called fovea, okay, and this is the blind spot where your optic nerve is connected. Okay. So, the dimensions and the quantities of the rod and cell cones, cone and rod cells can be seen here in this particular table. So, diameter of rod cell is around 2 micron, whereas cones are like 2.5 to 7.5 micron. Length for rods are like 40 to 60 micron, whereas cones are like 28 to 58 micron. And you can see here the quantity of rod cells are much larger, almost like 10 cr. Okay, rod cells are there, and there are around 65 lakh cone cells. Okay. Now, you have to understand that the rods are more sensitive than cone, and thus more easily they are saturated when ambient illumination is high. That is like when you get exposed to bright sunlight. So, rods are also sensitive to light intensity, but you have to remember that they are inert to colors. So, rod cells do not see colors. On the other hand, cone cells, they function well under bright light condition and they are color sensitive. So, all the colors that you see are basically because of this cone cells. Now, if you consider dim lighting condition, that is under low illumination, the rods basically dominate, and that is where you will be basically seeing a grayscale vision. That means you do not see any color perception when the illumination is very low. So, you can also think of this, that in night time, if it is very low lit room, you do not actually see any color, it is more like grayscale, right. Now, we have to understand also what are the spatial distribution of the photoreceptors in our eye. Okay. So, the cones which are color sensitive, for them the highest density is there near the visual axis, that is the central part of the retina, and almost you will see that no rods are basically in the central, or you can say in the visual axis, because the cones are basically occupying that region. So, this is the region where cones are very much in majority, and yeah, I think this is how they show it. So, this is basically the place, and rods basically increase in number and reach a maximum away from the visual axis. Okay. And then there is blind spot here, okay, that basically tells you about that there is no rod or cone cells in this particular region. So, this is the direction of the nose. So, you are basically moving away from the retina in this direction, right. So, the blind, as I mentioned, blind spot basically is located where the optic nerve basically passes through the retina. So, that place is devoid of rods and cones. Okay. Always remember that rods are always more in number. Total number of rod cell is around 10 CR, whereas cones are only like 65 lakhs. But you can see in the central region the cones are actually having the highest density. That is what they were basically trying to convey here. Now, under bright ambient light condition, eyesight becomes most sensitive within 10-degree viewing cone, and outside this region the colors become difficult to distinguish. So, what is the perception of a complete visual sense? Despite the blind spot, human basically perceive a continuous field of vision, because though there is a blind spot, but it does not come into your picture or your feeling all the time, because this can be avoided, and you can always perceive a continuous field of vision through your eyeball movement and rotation. So, you are basically capturing information from different angles, and your brain basically combines all those visual signals to construct a seamless scene. Okay. So, it is basically getting stitched in your brain to give you a continuous image. So, that blind spot is not creating any issue. Another important factor is the temporal response of the human eye. So, flicker experiments investigated how eye perceives the flashing light that flashes at different frequencies. So, at very high frequencies, or you can say at high frequencies also, your eye will not be able to differentiate between flickers. So, the flicker will basically look continuous, and that is basically due to the persistence of vision. And this has been used to create movies which are basically, the frames, the pictures are basically repeated at a very high speed to give you a continuous motion picture, right. So, different photoreceptors in your eye has different response time. So, cones, they have very short response time like 15 millisecond, whereas rods have around 100 millisecond response time. Okay. So, if you see among the photoreceptors, cones have around 15 millisecond response time, and rods have much longer, around 100 millisecond response time. So, critical flicker fusion rate. So, generally accepted range is around 50 to 90 hertz, where the flickers appear continuous, and now you can understand why your display rate of your monitor is typically set to 50 hertz or 60 hertz. Okay. So, under specific conditions, flicker artifacts may be perceived up to 500 hertz, but those are like specific cases. So, what are the display frame rates? Typical display frame rate is around 60 hertz. Okay. So, that aligns with the critical flicker fusion rate, and when I say 60 hertz frame rate, that basically provides 60 frames per second. So, it ensures a smooth flicker free visuals for human eye. So, what we can see, what we can perceive, that basically dictates the refresh rate of this electronic gadget that we are looking at. Now there are some challenges in moving picture displays as well. One is image blurring. Now this occurs in displays with slower response times than the cone cells. The cone cells have response time of only 15 millisecond. Okay. So if you have anything that respond slower than that, like LCDs, in that case you may see image getting blurred in the transition. Even with fast displays, something like OLEDs, where you have microsecond response time, that means the OLED displays can get refreshed very quickly. Human eye tracking may cause blurring. Okay. So motion blurring can be understood from this particular example. So here you have 4 frames and we are talking about 4 pixels, and this is the temporal domain. That means with time you are moving from frame 1 to frame 4, and in the spatial domain you are also moving from pixel 1 to pixel 4. So a moving pixel emits light during one frame but persists into the next frame, causing the blurred edge. Okay. So the blurring basically affects both luminescence or luminance and the color, and especially in field sequential colored displays, something like LCDs. So here what is happening, I believe you could guess that this bright spot is basically moving diagonally. Okay. So for the emission from pixel 1, that is in the spatial domain, during frame 1, that is in the temporal domain, the signal persists at pixel 1 location, okay, during the beginning of frame 2, okay, resulting in the image blurring at the edge of the moving object, even though the response time of the display is much shorter, okay, than that of the eye. So considering the color display, not only luminance blur, but the color may also change at the edge of this moving object on the display, which typically can be observed in LCD with this field sequential color displays kind of operation. So what are the methods to reduce motion blur? First thing is black frame insertion. So you can insert black frames between the display frames to reduce motion blur. You can also think of reducing the emission time. That means you can think of 4.2 millisecond for one 60 hertz frame, that is typically around 25% duty cycle. So the time the display or the light will be on is now only 25%, that means the duty cycle, the on time over the actual time period. And it also requires higher peak luminance to maintain the same average luminance, okay, because now you have reduced the duty cycle. Another aspect is the moving picture response time, that is MPRT. This quantitatively describes the response time for any moving object in display. So there is a formula that allows you to calculate this MPRT. It is basically BEW in terms of pixels, that is basically the blur edge width that you calculate in pixel, divided by V, that is the velocity of the moving object in terms of pixel per frame, times TF, that is basically the frame time calculated in millisecond per frame. So with that you can basically obtain the moving picture response time MPRT in millisecond unit. Now we also need to understand that rod and cone, because they have different response time and different sensitivity. So in your eye also you have spectral sensitivity regions, okay. So there are two regions, one is called scotopic, one is photopic, okay. So let us understand the spectral sensitivity in scotopic and photopic region. So the scotopic vision is mainly dominated by the rods, where the sensitivity is peak at around 507 nanometer, that is at the low light levels, and it is understood that the rods cannot distinguish colors. And then you have photopic vision. So, obviously, this is dominated by the cones. Here the sensitivity is around 555 nanometer. So, at high light level, so for high brightness, cones can deliver well. So, you can see using cones. Also, cones enable your color vision. So, what about overlap of responsivity? That means at intermediate light level, something like moonlight to indoor lighting, your rod and cone both can function simultaneously, right. So, the rods get saturated at high light levels. However, the cones become inactive at very low light levels. There are also different type of cone cells, and each type has a different spectral sensitivity, means they are responsive to a particular band of wavelength. So, S cones are short, medium, large, you can understand. These are basically corresponding to the wavelengths they are responsive or sensitive to. So, S cones are sensitive to short wavelengths, that is blue. M cones are sensitive to medium wavelengths, that is green. L cones are sensitive to long wavelengths, that is red. So, here you can see in the scotopic regions, okay, here you are basically, no, here this is basically for the cones, okay. L, M and S cone, these are the sensitivity regions. You can see short cones are mainly for the short wavelengths, that is the blue ones. M is mainly for the middle wavelength, that is around green, and L is towards the red, okay. So, these three cones, types of cones basically are responsible for different colors to be sensed. This particular figure shows the photopic and the scotopic regions. So, you can see this is the one which is scotopic and this is the one for photopic. So, what you see in this graphs is that rods and cones, they contribute to vision across a range of light intensities, okay. So, you can also understand that there is a transition, okay, between two types. So, here you can see this is the normalized sensitivity graph. So, at low light your rods are doing good, and then slowly the cones take over, okay. So, there is basically a transition between scotopic and photopic regimes, and the peak sensitivity also shifts from 507 nanometer, which is called for scotopic region, to photopic region based on the light condition, okay. Next is, how do you measure the visual acuity of eye? So, many of you might have done a eye test in a eye hospital or even in any ophthalmology shop or any eyewear or specs shop. So, there typically people use these letters C and E of different sizes and different directions to find out how good is your eye vision, okay. So, always remember there are some standards, something like a standard viewing distance is 6 meter, okay. So, standard visual acuity is 6 by 6 when you are talking in terms of meter, and you can also call 20 by 20. This is the imperial unit system used in US, okay. These are typically in feet. So, what you see here is the visual angle of the entire character, okay. So, that is typically like 5 minutes, okay. So, that is 5 by 60 degree, and typically in this particular E and C there are these gaps, okay. So, this gap is basically considered to be equal to 1 arc minute, okay. That is 1 by 60 degree, and that corresponds to 1.75 millimeter gap in the character when it is placed around 6 meter from your eye. So, this length, the length of your eye or you can say cornea to retina is around 17 mm. So, this is that 1 minute angle. So, this basically gives you a 5 micron area on the retina. So, how do you interpret this visual acuity ratios? So, when someone says 6:6 vision, that means, or you can also say 20:20, the ratio is 1.0, that corresponds to a normal vision. That means a person can resolve a gap of 1.75 mm from a distance of 6 meter. Okay, he will be able to differentiate these two edges, okay, very well. Now, if somebody has got this acuity ratio to be 6:12 or 20:40, or the ratio is computed to be 0.5, that person has reduced vision. That means that person can only resolve a larger gap, which is double than this one, that is 3.5, corresponding to a viewing distance of, or it can also correspond to a viewing distance of around 12 meter or 40 feet. Okay. If somebody has 6:3, that means the acuity ratio is 2:2. It means that person has a superior vision and can resolve much smaller gap, half of this one, okay, from a distance of 6 meter, right. So, what are the important parameters that you see here? This 1 minute angle. So, this is basically a gap of 1 arc minute, which is basically 1 over 60 degrees, that corresponds to 5 micrometer area on the retina. Okay. So, that is typically the diameter of a cone cell. So, the retina display concept comes from this thing that the pixel must be smaller than this work on arc minute visual angle, so that it is indistinguishable to a standard observer who has got 1.0 visual acuity. So, your pixel size should not be should be smaller than this, so that you cannot differentiate between the pixels, and that is where the concept of retina display has come up. So, display pixel size and density, how do you basically correlate? For mobile phone viewing at 25 centimeter, which is below 1 foot, okay, the critical pixel size should be less than 72.7 micron, okay, or the pixel density should be more than 349 ppi. That basically corresponds to a visual acuity of 1.0. So, this is how the normal requirement of a mobile display is fixed. Display pixel arrangement basically differs from the cone cell arrangement in human retina, obviously. Last and very important effect that we will see is the blue and the violet light effects. Now, the short wavelengths, they have high energy. So, if you go to any eye or eyewear or a spectacle shop, they will sell glasses with blue light protect. So, what is that with the blue light and what is wrong with it? So, shorter wavelengths basically correspond to high energy. So, when you talk about blue and violet light, they have higher energy and they can damage retina cells like rod and cone cells under high intensity or prolonged exposure. So, if somebody is wearing a regular glass or somebody is wearing a blue protected glass, the second person can view at their mobile phone much longer with lesser eye strain. Okay. So, circadian rhythm impact. Okay. So, it tells that the blue light, which has around 460 nanometer, or the full width half maximum of around 100 nanometer, it basically suppresses a chemical called melatonin, okay, the production of that chemical. So, it leads to sleep disorders. So, this is also known as blue hazard, and it basically highlights the health concern for coming from the blue light exposure. So, when you have melatonin suppression, though it is good and you can say it is beneficial during the daytime to maintain alertness and wakefulness for a person, but it becomes very bad at night because you will stop getting good sleep, and that is why the proper display usage becomes very important for your health. So, lighting and blue light content. So, when you do home lighting, typically you should use yellowish because it contains less blue light. So, that basically promotes relaxation and sleep. So, people go for yellow warm kind of light. So, if you these days want to buy LED bulb, you also get to see there are two options, cool daylight and the warm. So, warm will actually have lesser blue content. So, you can actually have more relaxation, and you can get good sleep when you are exposed to that kind of light. But when you go for workplace lighting, you want the blue to keep you awake. So, people go for white, the cool daylight one, or the bluish white, that basically helps you to enhance concentration. And now, let us look into the final thing, that is the 3D perception and displays for this lecture. So, what is a natural 3D perception? So, we understood that human eyes form different images and the brain basically combines them to perceive the depth, and the focal length of eye lens automatically basically gets adjusted by the ciliary muscles based on the object distance. So, you can actually think of all this together to create a 3D display that basically use different images for each eye to create the illusion of 3D. So, here the display is creating the illusion of a 3D object. Okay. So, the flat screens in devices like virtual reality headsets present images at a fixed distance, conflicting with natural lens adaptation, right. So, here the distances are fixed. So, but you basically conflict with the natural lens which try to adjust, right, with the distance. So, this conflict between the lens adaptation and the apparent distance for different images and object is called the binocular visual fatigue, and this can also cause discomfort if you are trying to wear a 3D display for a very long time, right, because actually in the virtual reality headset the image is formed at the same place. So, your eye will the natural lens will try to adapt, but you actually want purposefully to show one smaller and one larger to give that perception of depth. So, this conflict between the natural lens and the VR headset feature will give you this binocular visual fatigue that can cause discomfort if you use these headsets for too long. So, with that we conclude this lecture. Thank you for your attention. If you have got any query, you can drop an email to this email address mentioning the course name on the subject line. Thank you.